Welcome to another episode of the Distributed Data Show, brought to you by DataStax Academy, where we bring you the latest news and interview technical experts to help you succeed at building large-scale distributed systems.
This episode of the Distributed Data Show is going to be all about performance and benchmarking. I'm Jeff Carpenter. I'm here with Nitsan Wakart. So it's good to have you on the show.
Thank you.
I've been checking out your background a little bit, and you've done quite a bit in this area. So we're really excited to have you with us here at DataStax now. So can you just elaborate on that for me a little bit? How you came to be with us, and what you worked on.
So I used to work for a bunch of companies in the long past, but more recently or more relevantly to the kind of performance field, I used to work in finance, so pricing systems, trading systems, and so on. Where obviously there's a lot of focus on performance, which kind of drew my interest into profiling and analysis and the kind of different aspects of the performance engineering side of things. I went on from there to work for a company called Push Technology. They have a messaging product called the Fusion, which is where I was doing performance engineering as a full-time job for the first time. And from there, I went on to work for Azul systems on the Zing JVM. Doing performance engineering, focusing mainly on the JVM compiler output and ways to improve the performance of compiled code. So you write your Java code, and the compiler needs to make the best decision it can make given the profile it sees of your usage of that code into generating machine code that is appropriate for the architecture and appropriate for the classes you loaded, the available code, and so on and so forth. Which means I spent 3 years basically looking at a lot of assembly on the one hand and Java on the other hand, and trying to see where can we go into something a bit better on the right-hand side. Working for Azul, I got to know Jake from DataStax because I was working on Zing. Zing is used in a lot of use cases involving Cassandra. Mm-hmm. So I got talking to Jake about Cassandra's performance, and we kind of consulted each other. I then left Azul, went on to do some consulting, give some courses. We kept in touch, and we got talking, and he kind of pulled me in to work on the DataStax Enterprise 6 release, which came out just recently.
Yeah.
So I've been with DataStax for 6 months, pretty much full time, and amazing team and a great product. So here we are.
Cool. So this term of performance engineer is a job role that maybe new to some people as a discipline. I think it's a warranted kind of thing, given the large scale kind of systems. And the high performance requirements that we have on many of our systems. And it sounds like you've worked at, if I have this right, kind of at the application level, at more of the database or infrastructure level, and then down at the JVM level. Like you pretty broad swath of performance engineering experience. So can you elaborate just a little bit on kind of like what do you see as that role of the performance engineer look like?
So I think to me, engineering is about taking a systematic, analytic approach to a topic. And in that sense, performance engineering is about applying those kind of logical, scientific steps to software where we can say, this is what the software does, this is what behaves that way. And we can improve it if we choose to by taking these steps. And in software, there's I think computer science erred on the side of mathematics in the curriculum in universities and in a lot of people's approach. And that is from a philosophical standpoint, kind of a rationalist view where if I think it is. So if the code looks fast, then it must be fast. Where the engineering comes in is the real world steps in and ruins everything. So you have the situation where code that looks great just performs horribly,
Right.
And vice versa, code that looks horrible performs great. It's not always the case, but performance is quite often surprising and quite often related to many factors that are difficult to just rationalize out of thin air in your couch.
Well, how could
so
you?
you have to just go out there and make measurements and be methodical about it.
So you couldn't. I mean, with modern application development, you're relying on so many third-party libraries that you're probably using that you have little to no idea of what they're actually doing. And then what hardware are you running on? Is this shared hardware? Are you running in a cloud environment? How big of a slice of the time are you even getting from this virtual machine?
Yeah.
I mean, there's a lot of factors. So you mentioned the importance of measurement in this. And so I'll ask the question, when I think of performance engineering, probably the number one tool that comes to mind in your toolbox is the benchmark.
Yeah, that's
yes, no.
Yeah, definitely. And benchmarking have a really bad reputation in the industry because it is often it gets to a point where it's kind of a marketing tool. So there's a lot of pressure on people to show a result that puts them in the best light. And reality is often very complex. And talking about complicated things doesn't make great headlines. So you want to be able to go out there and say, I'm doing 10 million operations per second. And then going into the details of those are very small operations or very big operations. And what I mean by that is I have to use a massive machine with lots and lots of memory, or I'm doing it on a very small machine. These operations are very simple or they're very complex. All of these factors, the constraints that you have on what you're trying to do, they all play into it in a way that just doesn't make great headlines and doesn't make great marketing. So we're left with this kind of reductionist approach where you have to give people a headline on the one hand. On the other hand, because as a discipline, programmers don't have that experience with being methodical about measurement and approaching the topic methodically, we end up with a lot of benchmarks not actually measuring what they purport to measure.
Okay.
And the interpretations that people give to the results is often inappropriate. One of the sort of big names in this space is Gregg, who's a performance engineer for senior performance something or other for Netflix at the moment. And he's got tons of experience. He's got a great book called Systems Performance.
Oh,
and
yes.
It's a great reference book. I recommend it to anybody. And it's he has this quote where he says people benchmark A to measure B and end up measuring C or something along those lines. There's often this kind of chain of confused events where you end up measuring something that may or may not be at all relevant to the workload you thought you were measuring.
Right, and it may not have any basis in what you actually care about your application.
So you often see people perform some sort of throughput benchmark for network. And you would see them then take that number, let's say I sent 1 million messages per second, and they would say that means the latency is 1 microsecond. Now, to get 1 microsecond latency between two machines is actually quite difficult. You need specialized hardware.
Of course,
to have a kernel bypass. This is very, very unlikely that this is what they saw. What they did is they took a throughput number, they divided it by the amount of time and pulled a latency number out of that. And
that's bad math.
It is bad math, but it's also quite typical of the field. Now, add to that the complexity of the kind of the stack we all operate in, where you have your code, then in the Java world you have the JVM, you have the operating system, and you have the hardware, and maybe you have some sort of virtualization layer between the JVM and the OS as well, so between the OS and the hardware. All of that just multiplies the factors that feed into why did you get that result that you want to get, how come you got the result out of the experiment that you ran, and any number of factors can play into that, which makes analysis harder, which makes the reporting of results trickier, which means a lot of people are reporting results that are entirely meaningless to the domain they're in. So if you look for literature on Java benchmarks, you will find a lot of the advice out there is don't do it. Just don't measure, because you're going to get it wrong. And benchmarking is confusing and evil and should only be done by the top experts.
Oh, interesting.
So
is benchmarking evil?
No, I think benchmarking should be a necessary part of the curriculum, and I think the more people do it, the better they'll get at it, the more open discourse we'll have around results, and the more we'll evolve as a profession towards having a better foundation and a better methodology we can share with each other around that.
Okay, so what are the ingredients of good benchmarking, or if we could nutshell that methodology? Is I know that describing the conditions, all of the conditions as much as possible, is probably an ingredient. What else is there?
So you have to start with some understanding of the configuration in which you're running, the use case.
Yeah.
At the very basic level, what OS, what hardware, what JVM version I'm running on, all the pieces that are underneath your stack. There's a guy who works for Oracle, Sergey Kuksenko. He's in the performance team there, and he has a great talk online about performance, and he says performance is easy. All you have to understand is everything. By which he means you have to understand all the factors. But I think to start off with, let's just describe the hardware and the settings we're in, and we don't need to know the CPU internals to say this is the CPU I'm running on, and this is the OS I'm running on, and this version, and so on. Even capturing that bit of data would be a good starting point. You want to move on from there to have some baseline measurements of, this is the system at rest, this is the system on the some load. These are similar measurements I can take within this environment. You want to make sure that your lab is set up such that measurements are stable. You want to take lots of measurements to understand the variability in the environment and in your benchmarks. You want to try and get an idea of the statistics involved in the measurement. And this is where a lot of people fail, because they take for granted that kind of stability, the mathematical model of computing. You say, I'm running an algorithm. In my, in this theoretical world, every operation is with X, and I add it all up, and performance should be therefore Y. In reality, with the amount of moving parts underneath your software, it's very rare to get two measurements that are exactly the same. There's always going to be some variance involved. So, come up with a scenario, run it in a stable environment, and see what sort of variance you see, and then that's a good starting point. If everybody's starting from there, I would be much happier.
Yeah, and I would think that you would have to run a benchmark for over a long enough period of time that you actually can have some meaningful variation, like say, did you run it long enough for the JVM to go through a GC cycle?
Yeah, I think it needs to be long enough to be meaningful for your domain. And the more clever your environment, the longer you need to run it in a way, because part of the sophistication of the JVM is the fact that code starts in the interpreted mode and then gets compiled. Part of the sophistication of the underlying hardware is that your data starts off on disk and ends up in memory and in the cache system.
Caching, yeah.
So there's a warm-up stage, And in the JVM, there's a lot of heuristics involved in the code. So the JVM learns as you run your code, and as such, if you don't give it time to learn, you're not going to see the performance that you would get once it's learned. Now, is this relevant to every kind of benchmark you want to run on the JVM? Maybe you wrote a little batch tool that you're running for 3 seconds and then it's done.
Right.
Then that's what you need to measure. But if you're measuring a server-side system where it's going to be running for hopefully month before it falls over,
right,
or maybe it never falls over, never gets replaced in this kind of utopia, then give it some time to get to the point where it's more representative. And further than that, some situations take days to get to, especially when you're talking about large heaps with GC. Some GC algorithms, more than others, end up getting the knickers in a twist, as they say.
Right.
And 3 days in, you will have a very fragmented heap. You'll hit a full GC event that would take many, many, many seconds. Now, if you're only
this is when you really find what your tail latencies are.
if you're only measuring the first 5 minutes, 10 minutes, 15 minutes of your application, then you'll never see that. Granted, running your application for 3 days is a long time to wait for something bad to happen, and who knows? Maybe it takes a week, maybe it takes a month. But the running it for 30 seconds is arguably trivially too little.
Right.
So you have to kind of match the experiment to the reality you wish it would represent.
Right. Okay. So thinking in terms of, I think we've already hinted at this a little bit, but thinking in terms of performance engineering and running benchmarks on a distributed database system, and keeping in mind that we have just released DSE 6, and we ourselves have put marketing message out there saying, hey, this is 2 times as fast as our previous version, roughly. Well, that's on the shorthand marketing speech, but there is an apples to apples kind of comparison that's behind that. But what can you tell us about kind of what does that process look like, performance engineering on a distributed database like Cassandra, DSE?
So a lot of the tools we use are internal, so I don't think it helps to go into detail there.
But not the specific tooling, but the processes.
But in terms of process, what we do is we have a bunch of workloads that we look at repeatedly with each kind of mutation of the code. And if we want to build a new feature, we would test that with a set of benchmarks, and run it many times to see what sort of variance we see. Compare that to previous versions. Compare that with different configurations. The one thing that happens very, very quickly is your matrix of testing explodes because there are so many variables.
Yes.
And we test it on this size machine, that size machine, virtual machine versus on bare metal, even with different JVMs for different purposes. So you end up having to run the same scenario under many different conditions, just to get the different perspectives and the kind of to get the interesting data out. Something that works well on bare metal might be a disaster on a virtual machine, and vice versa. So you take all that, and then on top of that, we have the field engineers feeding in their feedback and their use cases. We have specific benchmarks we write to exercise particular scenarios that we think are interesting or would squeeze out conditions that are extreme enough to
So like tiny rows, large rows, really wide partitions, like what kinds of things?
Number of connections, number of requests per second, different schemas, etc. It all kind of feeds into making the observation that version A is better than version B. Now, if I'm honest, I'm uneasy with anybody putting a number on it and saying performance A is better than performance B, simply because performance is such a loaded word. What exactly do you mean by that?
What are you measuring?
But I can say that, well, for one, I think the saying it's twice as good is by industry standards quite a modest proclamation. It's
right.
You see far more extreme kind of expressions of joy out there. But more than that, I feel it's justified in some senses. So, for instance, DSC6 scales far better in terms of core count than previous versions. If you take previous versions of DSC and Cassandra and you compare how they would behave going from a machine with 8 cores to 16 cores to 64 cores.
Oh, okay, yeah.
DSC6 scales great, where DSC5 or Cassandra, I think it's the equivalent is somewhere at the 3, and just can't go beyond a certain point. So on the scalability side, I think it's way more than 2 times better.
Yeah. So you're talking about in terms of the ability to take advantage of running on machines with more cores.
Absolutely.
Yeah.
With more cores, with more memory.
Yeah.
On the latency side, we see a much better tail end latency, and we see a much better behavior of latency under load. So as you increase the load, the latency will stay down for far longer with DSC6 versus the original Cassandra. Now, where it becomes tricky, under very low load, you will get latencies. Again, it's within certain parameters and within a particular configuration. You will get latency that is similar or slightly better if you're just making 1 query per second or 1,000 queries per second. If the load is very, very low,
right,
then performance might not.
You're not going to see a big difference,
because part of the challenge we were tackling here is to make DSC6 better for higher load, better for scalability,
right,
better for bigger workloads. So if you're on the tiny scale, maybe we didn't help you that much. Maybe for you that proclamation...
Well, it was already pretty fast for that particular
maybe,
usage pattern.
All I'm saying is maybe on that scenario, the 2x performance doesn't materialize.
Oh, you're right. Okay.
Yeah, and that's where I'm, as a person who likes precision, that statement is kind of a broad stroke.
Yeah, you're trying to generalize the thousands of test cases into sort of a general...
I would like a 1,000-page document that we would say, this is the new performance, this is the old performance. And you can just go and read it. Yeah.
And that's fine, and that's what we as engineers need and want for our applications. Yeah. So let's take this up the stack a little bit. So I'm an application developer and I'm looking at distributed databases. How am I to evaluate the performance of different options that I'm looking at? What's your advice, recommendation on how to go about doing that? So should I just insert a bunch of ints?
Yeah, absolutely.
As fast as possible?
If that's what your application does.
Very good.
The problem with industry benchmarks is, and that goes for the JVM as well, if you look at spec JVM or spec JBB, and the same goes for distributed databases. If you look at YCSB or C-Stress and so pre-conceived workloads, they're very tempting for the vendors to try and overfit into. At the end of the day,
that's hard. Right. We tuned it for this particular benchmark,
and at the end of the day, how relevant is that workload to your workload? So if you're writing, a schema that is the same as the YCSB benchmark schema, and you're going to have a similar workload coming from a similar, setup, maybe it is relevant. But for most people, it's completely irrelevant. So if you want to know how a particular technology is going to benefit you in any real sense, you would have to custom build your workload. You can use C-stress and you can use other load generators as a starting point, but you're going to have to customize that to fit your workload, to fit your usage patterns, to fit your schema and your data. And you're going to have to go through the exercise of shoveling enough data into the system to make this exercise worthwhile and meaningful. And only then are you going to be able to say, this is the right direction for me, or this is the right product for me.
That sounds like a lot of work.
It is, but and I would love to say that in every case you will end up on on Cassandra or the C6 for that matter. But you may go through the whole exercise and find out that you've gone completely in the wrong direction. It is an investment, but if you want a meaningful answer to that question, that's the only way you're going to get it. Looking at how well a JVM performs on an industry benchmark, or a database performs on an industry benchmark, has very little predictive value, if you will. So you're going to have to do some work.
Yes,
sadly.
I gotcha. Well, that is always probably the reality and probably the advice that we would give to anyone. But in terms of advice that you would give to somebody who's interested in this field of performance engineering, I know you've mentioned a couple of authors, a couple of individuals that have influenced you. Do you have any other thoughts that you would share about how somebody kind of gets into this area and educates themselves?
So there's a bunch of great engineers who are on Twitter and some of them have blogs. In particular, there's Alexei Shepilov, who used to work at Oracle and now works for Red Hat. And between him and Sergey Kuksenko, and I'm imagining there's a few other people who were involved in this effort, they built JMH, which is the micro-benchmarking harness people should be using if they're benchmarking Java programs, and it enables you to build a whole range of benchmarks, from tiny benchmarks measuring the performance of very simple operations, or you can hook it up to bigger and bigger frameworks and have more meaningful benchmarks to work with. And what it does is automates a lot of the boilerplate involved in building a harness, and it throws in some excellent formatting options and a bunch of profilers you can use. So if you're in the Java kind of sphere of influence, even they have plugins for JVM languages, so you could be in Groovy, you could be in Scala. But if you're running on the JVM, you should be using JMH to write benchmarks.
That looks like a great tool, by the way. I saw a demo that you did that was an eye-opener. That basically kind of showing that when you do a sleep, it doesn't really sleep for as long as you ask for.
And that's the other side of it. You need to start. That's the childhood, the child engineer in all of us.
Yeah.
Take things apart and then try and put them back together again and see if you get the same result.
Right.
And often you won't, and then keep digging and stay curious about that. Again, JMH offers you a lot of help down that path. There's the mechanical sympathy mailing list that has a wealth of already existing discussions on there to read through, and there's a whole lot of experts on that mailing list. So if you have a meaningful question to ask, then people will very helpfully chime in. There's a whole lot of information available for the more JVM kind of geek kind of people on the JVM mailing list.
So you can take this pretty far, huh?
Yeah, you can get it.
Look,
you can get into the OS side of things, the JVM side of things, the hardware side of things. But there's a ton of information out there, I think, where you need to have the determination and the kind of inclination to go and measure stuff. And if you measure it and it doesn't make sense, don't be afraid to go up to people and say, I tried this out and didn't work out.
Yeah.
Can you help me
Here
out?
are my results.
I
What is going on?
Yeah, I thought I would do this and it would work out, and it didn't. And I invested the time into investigating it. Can you help me out? People are, in my experience, very helpful and very supportive. And that's actually, I think there's a lot of, not to discount it, but there's often a lot of self-beating in the industry about how terrible people are terrible to other people. And it's absolutely true that there are, there's assholes
Sure, it happens.
in every industry. But I think it's also important to celebrate the good people and the good behaviors in our industry, and those exist.
People that are willing to help.
Absolutely, and it's been my experience that a lot of people are willing to help. So,
yeah. Excellent. Well, I know that you're one of those, and I'm very grateful to you to coming on the show and your continued influence on performance engineering as a discipline in the industry, and your contributions at DataStax. So,
thank you very much.
All right.
Cheers.
Until next time.
Thank you for joining us again for the Distributed Data Show. We love your feedback, so go to the Distributed Data Show page on DataStax Academy and tell us what you think. You can also find us on the DataStax Academy YouTube channel, or find our podcast on iTunes, Google Play, or wherever you get great podcasts. While you're there, make sure and subscribe so you don't miss a single episode.